There it goes. That second to last one. And when I went through to balance that, we went through with aluminum, then we did barium, and then we did sulfate, and then we did nitrate. Because the standard method that we would do would break it down according to each element. And in this case, I didn't break it down to each element. I went with the metals, and then I went and balanced as the complex ion. I could balance it as SO4 on both sides of the equation because it stayed sulfate. If I start with SO4, but then at the end I end with SO3, I can't balance SO4 because it's changed its nature. Okay? So we can go through and balance some of our more complicated questions or balancing equations by balancing the complex ions. We don't have to balance based off of the element. Okay? Do we want to try and balance this one based off the element just to see? I kind of don't want to because I have a feeling it's going to suck.
I tried.
Okay, so there we go. We have our empirical evidence. Don't always balance according to the element. You can take advantage. As long as the complex ion shows up the same on both sides, you can balance based off the complex ion. Should we go through and balance this one again? I heard some yes. How many aluminums do we have on the left? And on the right? 1. So we have to fix that. The aluminums must balance out. How do we fix that? We'll change the coefficient in front of that so that we now have 2 aluminums on the right. Yeah? Barium. 1 and 1. I heard a no just in case. Did you see that 2? That 2 applies to what's directly in front of it. What's directly in front of it? The nitrate. Good answer. The parentheses are what's directly in front of it. It's applying to whatever's within those parentheses. Barium is not within those parentheses. That 2 does not apply to it. Make sense?
Why don't they just make it a 6?
So why don't we change this? And that's a good question, so I'm going to push it all the way. You can't just say never mind, back out of that one. Why don't we write it as that? BaN2O6. Doesn't that have the same number of elements?
You change the structure, wouldn't it?
Okay, what that starts to do is remove structural information. Remember, when we're trying to put together our formulas, we just kind of group our elements for the most part, but we're also including some structural information if we have it. Okay? The complex ions, we have it, we need to keep it. Okay? So by distributing that 2 in, I can make that new formula, but then is that obviously nitrate? Is N2O6 obviously nitrate? No. Okay? That could become a variety of other things, and that's losing information. So we won't distribute that subscript because we're trying to maintain that information. Okay? Good question. So our barium is balanced. We could jump to our sulfate. So where do we have SO4? On the left. Green was a bad color. Let's try this. We have SO4 written there. Okay? Some students will say, well, I have 4 of them because there's a 4 there. The 4 is part of what makes it sulfate. Okay, so that's like getting rid of the L in aluminum. Okay, that changes its character. So the 4 belongs there. I do, however, have a 3 coming afterwards. That 3 applies to whatever's in front of it. What's in front of it? I'll accept sulfate, but ideally we would hit the parentheses. What's within the parentheses? Sulfate. So I have 3 sulfates on the left. On the right, I only have 1. Is that balanced?
No.
So I have to fix it. How do I fix it?
Change coefficient.
I will change the coefficient in front of the barium sulfate on the right, and I end up with 3 sulfates now on the right. Nitrate. On the left, I have 2. Again, we got to be careful. That 2 applies forward to the parentheses. Nitrates within the parentheses. On the right, how many nitrates do I have? Isn't it just 3?
Oh, because of the 2.
I have to remember that that 2 also applies backwards to up to the mathematical operation. So that plus sign. Okay. So I have 3 nitrates in aluminum nitrate, but I have 2 aluminum nitrates. So the total number of nitrates is 6. How can I make 2 equal to the 6? I need a 3 as a coefficient in front there. This becomes 6. Now what do?
Check.
Check the work. Aluminum. 2 and 2. Barium. 1 and, or wait, really? That applies to everything afterwards. So it's actually now 3. And on the other side, that 3 applies afterwards. 3. How many sulfates? 3 and 3. Remember that 3 on the right applies afterwards. The 4 is what makes it sulfate. So there's 3 of those. And then nitrate, 6 and 6. What do I do now?
You double check.
You check your work. And again, and again, and again, and again. Okay, until you hate me. Okay, just barely hate. Okay, that's what we're aiming for. Okay, so balancing equation should be something that you either know that you got right because you've checked your work, or you know that you've got wrong because you checked your work. Okay, so you should leave the test either super confident on your balancing or super unhappy because you knew you got it all wrong. There really should not be an in-between. And that's going to come with practice going through those rules. Okay? So if we clean that up a little bit, let's just erase everything. Whoops, I forgot to write down what the numbers were. Shoot. 1, 3, 2, 3. So if that is now the balanced equation, what questions could I ask? The sum of the coefficients is the most common question. That means taking each and every single one of those numbers, 1 plus 3 plus 2 plus 3, which gets us 9. Okay, make sense? So in that sum, don't forget that you will have implied ones. Not a bad idea, just show the 1 regardless. That way you won't ever forget that it's there. Okay, make sense? Anybody balance the last one?
Attempted, but then I stopped.
Attempted and then stopped. Okay, take a second to balance it. So yeah, when you take a look at that last one, what should you notice? It is actually balanced. Okay, but this is one that we could go through and walk through real quickly. We could say, well, hydrogen, how many hydrogens do I have on the left?
1 or 2.
2. That subscript applies to what's directly in front of it. On the right? 2. Okay. Oh, I see a complex ion there in carbonate. So I'm going to try and balance carbonate, CO3. Am I allowed to do that this time? Why not? There's not a carbonate on the product side, so I cannot balance the complex ion. I must balance as the elements. Carbon, 1 and 1. Oxygen, 3 and 3. Turns out it is balanced. Okay, make sense? Okay. What?
We can do more of those if you want.
Yeah. I swear there was a thought that I was going to ask, but I forgot it. So.
3 on the right side?
Yes. 3 on the right side. The 2 in CO2 applies to what's directly in front, which is the oxygen. That gets us 2. Then we have another oxygen in the water. That gets us 1. 2 plus 1 gets us 3. Okay. Relatively good? There was a question. What was I going to ask? Clearly wasn't important. So, classifying chemical reactions. In theory, you watched a video on this that summarized all of these. Okay? What this one slide does is try to show all of the chemical reactions you're responsible for, minus one, the combustion isn't on there. Okay? These are the 5 primary chemical reactions that you're responsible for. So when you look at a chemical reaction, you need to be able to say that is a decomposition reaction. That is a single replacement reaction. That is a double replacement reaction. You have to be able to pull that information out, okay? For a couple reasons. When it comes to those reactions, some of them you are expected to be able to predict the products of. So if you're only given the reactants, you need to be able to decide what the product is. Okay? So you have to be able to look at the patterns or find patterns within these so that you know how to and when to predict. Okay? And that gets a bit tedious. Sometimes students kind of freak out and say, well, I can't possibly do that. Okay, well, let's go through and take a look at these. If I was to look at a combination, or the combination pizza, what's on the combination pizza? Everything. I combine everything, put it on a pizza. So what's going to happen in a combination reaction? I'm going to combine pieces and I'm going to put them into one thing. So I start with 2, and what do I end with? 1. What happens with the decomposition? If I decompose something, I'm taking it apart into the individual pieces. So I will start with one thing and I will end with 2. Okay, I already heard a key word here. Decomposition reactions are the reverse of the combination. Okay? So you're just trying to look for patterns on what you're starting with, how much you're starting with, how much you're producing, how much you're not producing, all that kind of fun stuff. Single replacement versus the double replacement. Okay? Or ultimately even back to the combination. In the combination we start with 2 things. How many things do we start with in the single replacement? 2 things. I'm hearing a 3 there. There's really only 2 things. Okay? There's A and then BC. What is BC? 1 compound. But that 1 compound, when it reacts with A, splits. And it becomes, wrong eraser. We end up exchanging A and B. Okay? So if we looked at the combination reaction, we're adding 2 things with each other, but it's really 2 pieces. When we look at a single replacement, I have 2 separate structures where one of those compounds has multiple components. I'm exchanging similar components within them. Okay? It's like if you took your car into the shop, you can get new tires on your car, right? It doesn't mean they burn the whole car. Okay? And give you a brand new, that would be nice. And give you a brand new one. No, they take off the old ones and put new ones on. Okay? They've done a replacement of parts. Okay? That's effectively what's happening in the single replacement. Okay? Except in that analogy, the single replacement, they replace 1 tire. That's not very helpful. Okay, what about the double replacement? We're then, again, with 2 pieces, but each of those pieces has parts associated with it. And when we go through and look at the results of that, we end up exchanging both pieces. Okay? The neutralization, again, 2 pieces. What stands out is kind of different in the neutralization in comparison to all the others? We are specifically referencing hydrogen, and we are specifically referencing hydroxide. Okay? If we added a little bit more information, you would typically see this written as HAAQ, meaning acid. Okay? Acids are dangerous. What do we typically do to acids? We neutralize them doing a neutralization reaction by adding a base. What defines our base? The presence of hydroxide in this class. Okay? If we look at the result, what happened?
Everything combined. 2.
We still got 2 things, so we can't say everything combined. The hydrogen and hydroxide combined. And? They made water, yeah. That's what happens when H goes with OH. And A and B combined. What kind of reaction do we do? And if you tell me neutralization, I won't do anything. It's kind of a double replacement. It is a double replacement. Okay? Why are we specifically or pulling out our neutralization reactions as a separate reaction if they are double replacements? Before you came into this class, have you heard of acids? Okay? Yeah. Acids and bases tend to be very well-known chemistry. They're so well-known that when we do acid and base reactions, we give them their own special name. Neutralization reactions. Right? That's why they're getting pulled out. Right? They're just that well-known. Right? So, you're looking for those patterns, trying to recognize them and move through it. I did add some extra information. We've got some color coding with blue and red. It's not perfect, okay, but the examples given here with the blue and red color coding are the most common that you would experience. Okay? So let's take a look at the neutralization, for instance. Okay? What charge is hydrogen typically? A +1. What would be bonded to a positive atom? A negative atom. So A we would likely predict to be negatively charged, non-metal. Ooh, good, dang, that was a big jump. Okay, sorry, I thought that was pretty awesome, good job. A non-metal, okay. We would reference the negatively charged atom as what? An anion. Oh, look at the color coding, okay. If we went through and took a look at the single replacement, A, being color-coded as blue, is what? A cation. If I'm going to do the single replacement reaction, what would I expect A to replace? Okay, B. Okay, fair enough. Why are you saying B? Because they're both cations. Okay, we're exchanging the same piece. The same chemistry is swapping out. I would never partner up and get A bonded to B. Why not? They're both cations. That's like charges repel. What happens when we move to the double replacement? You notice in a double replacement, I don't have as a possible product. Sorry, I actually got to look at this. AC, is that right? Yeah, and BD. Why is that not a possible answer? A and C are both blue, and the blue ones are specified as the cations. They have similar charges. What happens when those similar charges get near each other? They repel. That is a bad replacement reaction. Make sense? So you're trying to find the most similar pieces and exchanging those pieces with those reactions. Okay? So, on an entirely different note, nomenclature. Let's go ahead. I'll do it how I would have set it up. Whoops. I would probably, good idea to start the pen. But I broke my computer. Don't break. Are you going to let me write now? There we go. Oh, you can already tell how bad I'm a speller. Cadmium. Cyan. Not saying that's right, just so don't get too excited.
That's where we're starting.
Carbon, oxide, chromium, oxide. And now I get excited because I like these ones. Tetra was the oxygen. Di was the nitrogen. Same kind of deal here. Tri-carbon. Dioxide. I should have changed the color so we could see me do different things. Cadmium is a +2. Ooh, that was one I was told that I needed to memorize, so I will not specify the charge. The amount of cyanide is implied because of balancing a charge, so I don't actually need to write di. That one's actually done. Chromium oxide. Chromium is a +3. Oxygen I needed to memorize is a -2. Charges don't balance out right now. So I need different amounts of those. The easiest way for me to see those match out would be 6. So if I had 3 of these, 3y, what do I get? 3y minus 6 equals 0, y equals 6/3, 2. X was the number of oxygens. Got it? So, again, if I have the option for multiple things, I will just purge information. Okay? I don't need to get it right on the first try. I just need to get the right information down. Okay? Particularly if I have multiple choice. Okay? Now I'm nervous because you're telling me I'm wrong. What did I screw up?
No, I was just asking. So
Okay, good.
why would I be wrong if I put cadmium tube cyanide? Because isn't that just, since it's implied, is redundant information?
So that 2, if we put in the Roman numeral 2, is that incorrect? No, cadmium is a +2. Is that wrong? Yes. You are specifying information in excess of what was necessary, and because of that, you're wrong. That is not my rule. Okay, but that is how nomenclature works. You are not allowed to specify more information, even if it is correct. Okay. And you might say, well, why? Okay, well, cadmium melts at 302 degrees Celsius, so this should actually be, well, I can't say cadmium. Cadmium cyanide melts at 302 degrees Celsius as a melting point. So the name of CdCN2 is actually cadmium cyanide 302 degrees Celsius MP. Okay. Oh, it's also a white powder. So the name of that compound is actually cadmium cyanide 302 degrees Celsius melting point white powder. Do you really want to list all of the true information associated with the compound? That's a not happy argument to be making, but that's kind of the level we're going towards. Okay? So even if it's true, you can't specify it, okay, if you're not supposed to. And don't quote me on the 302 and the white powder. I have no idea. Other questions? Okay, continue to work with it. You've got that lab packet, do the lab packet. I cannot stress this enough. Okay, what I would argue you should do is you go, sorry, I'm going to steal that from you. Thank you.
That's fine.
Go to the tutoring center. You've got the pink sheet that lists out all the rules on how to name things. On the back, it gives you a flow chart on how to move through it. So start with your compound, move through the flow chart. Say, oh, it belongs to that compound. It's supposed to be a binary ionic. Flip over, find your binary ionic rules. Most people have a hard time and don't take this the wrong way, reading. Okay? And that's because your eye will tend to flit all over the place. Okay? As it flits, as soon as you see binary ionic, you're now reading something over here saying something about how to name ternary compounds. Okay? It's not a ternary compound. So reading that information doesn't make sense. So what could you do?
Cover the rest of it.
If you know it's a binary ionic compound, cover up the rest of it. Now when your eye flips around, the only thing it sees is the directions, okay, for that specific one. Make sense? Okay. Yes, that may seem a bit silly, okay, but until you are good at nomenclature, you should do whatever it takes to make sure you're consistent and good at nomenclature.
C3, is that where you got the tricarbon?
So when we're looking at the next one, carbon is a nonmetal. Oxygen is a nonmetal. Both of those things say nonmetal. Okay, which means the compound I'm looking at would be the binary molecular. The rules for binary molecular, there's no more Roman numerals, but I will specify the amount of every single element in that compound. The specified amount for 3 is tri. We go to the Greek prefixes. Okay, so it becomes tricarbon dioxide. Make sense? Okay. Please do lots and lots of practice on this. Because in theory, by the end of today's lecture, we'll actually get into the part that, yeah, can make it worse. Okay? So, combination reactions. Within the video, I think I only looked at the first one, the reaction of a metal with oxygen. Were you guys okay with that one? I'm going to take that as a yes. The blue one. Okay, when we're looking at a combination, we're combining two things to make something else. So the reaction of a non-metal with oxygen as opposed to a metal. Sulfur solid reacts with oxygen gas. So if we were to write that down as a formula, what is the symbol for sulfur? S. What is the symbol for solid? S. What is the symbol for reacts with? Plus. Symbol for oxygen gas? O. And gas, why are you telling me I need that too? Certain elements are diatomic. Have no fear of ice cold beer. Oxygen was one of those. That's the of in that statement. Okay, which means when we have oxygen all by itself, it must be written as O2. Okay? To produce, there's our reaction arrow, and we have sulfur dioxide, SO2. Notice I didn't give you the phase, which means
We don't need it.
don't write it. You don't know what it is, so don't include it. Okay? Within this one, how is this one different from the red one? Okay, and I'm gonna, actually, what's your question? Did you have a question?
I'm sorry.
No, it's okay.
I did stretch a little bit, sorry.
Oh, okay, that's even better. What is different about solving this blue one in comparison to the red one? So there's the red one, magnesium metal reacts with oxygen gas to produce ... question mark. The red one, you were being asked to predict the product. The blue one, you were not. Why in the red one were you being asked to predict the product? What is the identity of the product? It's magnesium with oxygen. Why are you being asked to predict that product? It's an ionic compound. Because it is an ionic compound, that goes back to your ionic charges. Are you required to know the charges on metals, particularly magnesium? Yes, you are required to know it is +2. Are you required to know the charge on oxygen? Yes, it is a -2. Is that formula correct? Yes. You have the ability to predict that one. Why do you not have the ability to predict this one?
Because
Sulfur and
Sulfur and oxygen make a binary molecular compound. How do we determine the amounts of each of those elements in it? We have to be told it. We don't solve for it. Okay? So when we're looking at the molecular products, we can't predict those, or we don't expect you to predict those because they're too hard to predict. We can get a bunch of different possibilities. Okay? That said, when it comes to combination reactions, we don't expect you to predict them at all. What we do expect you to do is be able to recognize they're a combination and balance them. So let's just go to the last one, the reaction of a metal and a non-metal. Formula for how do we start this one? Lithium metal is Li. Metal is a solid. Reacts with bromine gas. Br2 because beer. Okay, right? Ice cold beer. It's one of our diatomics. To produce, well, I put lithium, and I will put it with bromine. Should it be LiBr2?
No.
Why not? When we're predicting our products, we have to make sure our product is what charge? Neutral. What is the charge on lithium when it becomes an ion? A +1. What is the charge on bromine? -1. How much lithium and bromine do I need to balance out that formula? One of each. Lithium bromide is now my correct final product. Okay? Yes.
So do you only, like, you don't have to transfer over the two because the bromine has to be with something, right? It doesn't necessarily be with itself, it's like with something, right? Is that why you don't bring over the two? Or?
Why is the 2 present when we're looking at Br2? The 2 is necessary to make that elemental bromine. Do I have elemental bromine in the product?
Oh, so it's already included.
No.
It's
It's a different thing. It's not elemental bromine, so the 2 doesn't belong there, because the 2 means it's elemental bromine. So I can't bring the 2 across for that reason.
Because then it looks like there's 2 bromines, right?
So now we run into an interesting question, which is where I think you're going with that. Is this the correct equation? No. If we think back to the rules that we started with, you have to go through and predict your products, make sure your products are balanced. We've done that, and now what do we do? Balance the equation. Is the equation actually balanced? No. To balance the equation, what do we need to do? I will need 2, whoops, I wanted a different color there. 2 in front of the LIBR, so that now the bromine balances. But now the lithium doesn't, so what do I need to do? Put a 2 in front of the lithium on the other hand side. Now my equation is balanced. Okay? So this can scale very, very quickly. Okay? And the question that I could have asked is, what is the sum of the coefficients of the balanced equation if lithium metal reacts with bromine gas to produce something? You have to predict what that something is. You have to balance that something. You then have to balance the entire equation. Now you can answer the question. Okay? So this can scaffold very, very fast. That's why you need to be good at each of the individual steps. Make sense? Don't panic. I don't ask that all that often. Okay? I don't think I've ever asked that, actually. Are there questions? Yeah, that's possible. Are there questions about combination reactions? Decomposition. Again, we are not expected to be able to predict these. Okay? Under certain circumstances, the textbook presents, maybe we would be able to do it, okay, given kind of sharp guidance. You're not expected to on the exam. Okay? I believe we saw the red one in the video, so we'll skip to the blue one. Metal hydrogen carbonates decompose to give a metal carbonate, water, and carbon dioxide. And this one I'll give you a couple minutes to go through and solve. I want the equation for what does sodium hydrogen carbonate decompose into. So the official question is just what's the product, but I want the whole equation. Write out your whole equation. We are given information on how to do this reaction in that first statement. Okay, so it's now just a question of interpreting that. It says metal hydrogen carbonates. Okay, well, a metal hydrogen carbonate. What is sodium? A metal. So if I take a metal hydrogen carbonate and decompose it, what does it turn into? Well, it turns into the metal carbonate. What was my metal? Sodium. CO3, because that's carbonate. Don't panic and start yelling at me yet. Okay. Plus water, which hopefully we remember to be H2O, plus CO2, or carbon dioxide. Okay? Before we start jumping into trying to balance the equation, we have to make sure that the products we predicted were correct. Is carbon dioxide, or CO2, the correct formula for carbon dioxide? Is H2O the correct formula for water? Is NaCO3 the correct formula for sodium carbonate? No. Okay? And for those people saying, well, how do you know that? Well, what is the charge on sodium? What is the charge on carbonate? -2. If I have one sodium and one carbonate, the overall charge on that molecule is -1. When we're predicting our products, they must be neutral. Right? How many sodiums, how many carbonates do I need to make sure I get a neutral charge? I need 2 sodiums. Notice I'm placing the 2 into the formula as a subscript. And we said, no, you can't ever do that. You can't overdo that when balancing an equation. Are we balancing the equation? No, we're balancing the formula. We're absolutely allowed to touch the subscripts when balancing a formula. Right? We're making sure that is correct. Now that our formula is correct, now we can take a look at the whole equation and potentially go through and balance it. Okay? Our longhand on balancing. Sodium, how many on the left? 1 and 2. Doesn't balance. I need 2 over here. Drop the coefficient. Okay. I will skip to, interesting. Should we get away with trying to balance carbonate?
No.
That one's tricky. Why is that tricky?
We have the CO2.
I have carbonate on the left and carbonate on the right. So why can I not balance carbonate? Where did that carbon come from? From one of the carbonates. Okay, so we can't balance carbonate. We'll have to balance it out as the individual elements. How many carbons on the left? 2 on the right. 2. Hydrogens on the left. Yep. 2. There's 1 in the sodium hydrogen carbonate, but there's 2 of them. On the right. Oxygen's on the right.
6.
Yeah, that was fun, wasn't it? Everybody stumbling over themselves. 3, 1, and 2. And on the left, it was still 6. What do we do now? Check it. What do we then? Check, and check, and check, and check, and check, and check, and check. Okay? We now have our correct, fully balanced equation. Okay? Because I asked you to do that ahead of time, that's why you would go through and do it. For the sake of this question, what does sodium hydrogen carbonate decompose into? Well, CO2 and water and sodium carbonate. And we'd have to make sure that 2 is there. So as a possible, let's see if I come up with at least 4 multiple choice answers. Which of the following are valid for what sodium carbonate decomposes into? If I was to ask this question. I wouldn't, because you aren't expected to predict it.
Definitely B.
Okay.
Do we have to state the phase?
Do we know the phase? Okay. We could make the argument that we know the phase for the water and carbon dioxide. I would argue that you actually don't. The phase for water is actually gas. Okay. So if the phase information isn't specified, don't panic on it for your decompositions or your combinations. We will encounter phase information when we talk about our single replacement reactions. Okay. This gets into the oxidation state and charge aspect, or leads into it. So we'll see how far we get. We knew, big red letters, you must predict your products with a single replacement reaction. You are expected to do so. Okay? So I keep not fixing this freaking slide. So let's ignore the words, because Mike clearly can't read or write. Let's look at our formula. Zinc solid reacts with lead sulfate aqueous to produce what? Okay. Zinc sulfate. So we know that this matches our formula A. We have a B and a C. We have 2 parts to lead sulfate. That's why we say lead sulfate. Name each of those parts. So that matches the formula or system for single replacement reactions. The question then becomes, which 2 species should exchange? Should I end up with sulfate and zinc lead? Okay. This comes from recognizing patterns that come out of this. We are exchanging the things that are most similar to each other. What is zinc? A metal. What is lead? What is sulfate? Non-metal. Which things are most similar? The 2 metals. Exchange the 2 metals. I will end up with lead plus zinc sulfate. Okay? We do need to take a swing at phases. Notice when we started with a solid and an aqueous. The thing by itself was a solid. When we move to our products, we have a thing by itself and something else. What's the thing by itself? A solid. And the thing, or the not thing by itself, that one will be aqueous. Okay? So we are expected to be able to predict those phases on it. Did we predict our products correctly? What is the formula for lead? PB. I wasn't trying to be tricky. That's it. That's the formula for lead. What is the formula for zinc sulfate? That one's a little bit trickier. I have to make sure the charges balance out. What is the charge on zinc? A +2, the charge on sulfate, -2. Is that formula correct?
Yes.
Yes. Yes, Sky.
How would you know when to do these things? You know, I mean, like, how would you separate when to do like when to swap them, or like versus the last one?
You are looking for certain patterns within them. So if we take a look at, say, the last one, how many things did we start with? It was a decomposition. We started with one thing. How many things do we have here?
Okay.
2. So I shouldn't be doing a
Yeah.
decomposition. Okay? The single replacements will have probably an added bonus to them. We expect you to be able to predict the products, which means more than likely in the question it says, what are the products for this reaction? And you go, well, it's not a combination, it's not a decomposition, because I'm not expected to predict those. That can help you eliminate some of those answers. Make sense? Okay. So we good with that? Kind of make sense? Okay. We end up introducing a new concept here, the activity series. Okay. What the activity series is referencing is the reactivity of an element. Okay. We have to be careful reading the activity series because depending on who writes or generates the table, they organize things differently. Sometimes they'll show the most active up top, sometimes they'll show the most active down below. Okay. It's irritating. We just have to deal with it. So read the table carefully. If we notice here, they're saying decreasing activity, which means which element is the most active on this table? Lithium, the least active? Gold, being at the bottom. How would we manipulate and use this for our reaction? Okay, so when we write out our equation here, we had our Pb plus our zinc sulfate. I'm going to ignore the phase. I want to decide, did this reaction actually occur? I've predicted what would happen if it occurred, but did it occur? Okay. Everybody kind of understand what just happened there? Some fancy footwork over the words. We've predicted if it possibly occurred, this is what would happen. But if I mix these, did it actually happen? Okay. It is possible that you could find a mate. Does that mean you will find a mate? Wow, you guys are optimists. Okay. What we want to evaluate is, does this reaction occur? To do that, we have to evaluate the activity series and understand something about activity. The more active the metal, the more it wants to be partnered with something else. Okay? So lithium, on its own, is incredibly reactive. Meaning if we touch lithium, it melts us. Gold, on the other hand, being the least active, wants to be by itself. Which means when we touch gold, nothing happens. Okay? Interesting. Have we already taken advantage of this, say, in our everyday life? How many of you have lithium jewelry? Okay. We use gold for our jewelry because what happens when we wear gold rings? Nothing. It just looks pretty. That's nice. We aren't trying to mutate ourselves in the process of wearing the jewelry. Okay? We can apply this back to our reaction. Okay? We have zinc and lead. So we find zinc and lead in our chart. We got zinc here, and we've got lead down here. Which one is more active? Zinc. Because zinc is more active, it wants to be in a compound. So let's look at the equation. Where is zinc in a compound? On the product side. Which means, do we expect this reaction to occur? Yep. That's where zinc wants to be. It wants to be with something else. That's how we're interpreting this. Okay? Because you might hit this curveball, I think, after spring break. Okay? We don't necessarily have to show these partnered up with their ion. I could also go through and say that this is lead plus 2. And this is zinc plus 2. Okay. Well, now how do we use Mike's little handy dandy, it wants to be partnered with something? Neither of them are partnered with anything, so that makes it more difficult. So we can use the partner rule, or what we could go through and do is say, which one is charged? The more active the metal, the more it wants to be charged. Zinc wants to be charged. Where is zinc charged in the equation above? Only on the product side. On the reactant side, what's its charge? 0. What's the charge on lead in the product side? 0. Interesting feature. What happened to the charge across the reaction, or for each species? It changed. How does charge change? Gaining and losing electrons, also known as reduction and oxidation, okay? Which is where we have to look at oxidation states. Okay? Before we shift that far in, let's take a look at a couple examples here. I'll give you 3 minutes. This should be your skeleton answer. You've done the exchange. We haven't checked to verify did we do the exchange or predict our products correctly, but we've done the exchange in all cases. Okay? Magnesium and nitrate. Did I predict that formula correct? Okay, no, because magnesium is a +2 and nitrate is a -1. So I did not balance that formula correct. To fix that, I need parentheses around the nitrate and a 2. Okay? Now that formula is correct. Is that 2 the same as the 2 found on the other side of the equation? No. Why is the blue 2 present? I have the 2 in nickel nitrate to balance nickel. That's why there's 2 nitrates. When I go over to the product, why is the 2 there? To balance magnesium. I have a 2, I have parentheses, they all look identical. The intent on why they are written is entirely different. You cannot just copy blindly across. You have to think about why it was written there to begin with, which becomes more relevant when we move to the next one. When we do the double or single replacement, we get our silver chloride and our aluminum. Is silver chloride as a formula correct? What is the charge on silver?
+1.
A +1. We know that because memorized. Chloride is
-1.
a -1.
Put this through.
Okay. I heard a point here that there are 3. Are there 3 chlorides in silver chloride? Okay. It's +1 and -1. There's only 1 chloride. They are balanced 1 to 1. Okay. The gut instinct is there was a 3 over on the other side of the equation. Why was there a 3 next to the chlorine in aluminum chloride? To balance aluminum. When you go to the product, is chloride with aluminum anymore? No, so the 3 makes no sense. Okay? Just because we have numbers doesn't mean they move with everything. Okay?
Do we need to predict the states?
Officially, yes, but we'll back off of that and not worry about it. Okay? Last one. We did our double replacement. To figure out and balance our formula of gold sulfate, we need to know the charge on gold. And you all memorize the charge on gold, right? Ooh, ouch, you don't know it. So how do we do this one? Okay? I would argue, yes, that you don't. That's getting recorded. We can't officially do that. That's not the line. Okay? The official line is that if you don't know it, make it easy. What do I mean by make it easy? Make it equal to whatever we needed. What did we need for that to balance? We needed a +2 to balance out the charge on the sulfate. Okay? Don't like it, ultimately, sorry, don't care, you got to do it. Okay? I will always try to set up my equations, okay, where they balance out. That's actually why the text keeps getting erased, because if you look at the text and try and solve that one, it runs into the same issue that this last one does. Okay? We can't predict that because we don't know the charges.
You're just implying it then, since that's -2, that would be positive.
You're just kind of assuming that that gold is becoming a +2. Okay? You're making it as whatever's easiest for you to go through and solve.
Even though you're not writing anything.
True. You're not writing anything, but you need it to balance your formula. Okay? So if the gold was a +3, this formula is incorrect. So to predict your product correctly, you officially need to know the charge. Okay? Are all of those correct?
Yes.
This last one's actually wrong. This one's actually wrong. Because those answers are no reaction. And I conveniently erased that. I wonder if I can undo that. Can I undo back? No, I just deleted all my work. That's even better. Why are those last two no reactions? We're looking at the activity. We're comparing silver to aluminum. Which one is more active of those two? Whoops. Aluminum is more active, which means aluminum wants to be in a compound. Where is aluminum in a compound? On the reactant side, which means, does the reaction go forwards? No, no reaction occurs. How about the last one? Gold is the lowest one on the periodic or the activity series. Copper is somewhere up above it. Copper is more active. Copper wants to be in a compound. Where is copper in a compound? Starts in a compound. No reaction occurs.
Because you can't. No reaction occurs because you can't flip it because it has to be with.
Because of their activity, you can't flip them. Yep. All right, which brings up an interesting question. To go through and predict these, we needed the activity series. Do I expect you to memorize the activity series? No. Take a look at your very first exam. There's a little activity series written on it. It's actually already there. Okay? It won't be the entire one. It won't have everything that you need. Or it'll have everything you need and then a bunch of extra stuff just to be in the way. Right? Just because you're packing up, why is it bad, or why do we have gold as our currency? Because it's not active. Well, why is that a big deal? Let's imagine lithium was our currency. What does a terrorist come along to do to Fort Knox? A bunch of water balloons. And what happens? The sodium or the lithium reacts with the water, turns into an ion, and dissolves into the ground. There goes our international currency. Okay? Some metals are so active that they react with water and immediately stop becoming solids. Okay? Don't stress a whole lot about the superactive metals, just be kind of aware of them. We will pick up with the oxidation states in chapter 17 on Tuesday. Yes, that one is challenging. Watch the video ahead of time.